Welcome to the Problemers channel, Season 2, Episode 6, the episode in which we will discuss the solutions of the mathematical problems S2M8 and S2M9. If you're joining our channel in the middle of the season, then it is highly recommended and it's a good idea to find on the homepage of this channel the episode titled The Problemer Channel How To, and watch that episode in its entirety, because in that episode we explain everything that is going on the channel, and the material presented in that episode motivates everything that we do on this channel and explains why we do what we do. Meanwhile, we will come back to the solution of the mathematical problem S2M8, in which, as a reminder, we're given a trapezoid A, B, C, D, whose diagonals A, C, and B, D intersect at the point O. And we're also told that the circle S1 passes precisely through the vertices A and B of the trapezoid, and the circle S2 passes through the vertices D and C of the trapezoid in such a way that the circles S1 and S2 intersect precisely at the point O and the point M, with the condition that the point M is located exactly on the base of the trapezoid AD. And the objective in this problem is to show that the triangle BMC is isosceles, with the lengths of the sides MB and MC, as shown over here, being equal. Again, right now we are in the middle of studying the mechanics of the reverse order problem solving approach. We know that this approach has two flavors, the mechanical flavor and the heuristic flavor. And in the episode Season 2, Episode 3, and Season 2, Episode 4, I explained in detail how overall the reverse order problem solving approach works. Again, if you missed these two episodes, it's a good idea to watch these two episodes in their entirety. And in this episode right now, I will only analyze how the heuristic flavor of the reverse order problem solving approach can be applied to the solution, or to the search for a solution of the problem S2M8. Again, according to the heuristic flavor of the reverse order problem solving approach, we are suggested that instead of starting our reasoning with what is given and constructing a forward flow of causality towards what is sought after, we temporarily suspend that effort and work in reverse order by taking what is sought after is an input and trying to craft a chain of implications, if P then Q, they take us precisely from what is sought after towards some material that is given. And the idea is that on that reverse order journey, we may collect enough useful tactical insight that will allow us to put together a traditional or a sought after forward flow of causality. As such, in this problem, we are asked, given the material that was explained later, we are asked to show that the triangle BMC is isosceles, with the lengths of the sides MB and MC being equal one another. Consequently, trying to apply the heuristic flavor of the reverse order problem solving approach to the process of searching for a solution of this problem, we take that fact as given. In other words, we temporarily assume that, for example, the mathematical oracle did something to the given material and said, here, the triangle BMC is indeed isosceles, go. As such, if we model this initial input material with the point like this one, for example, then assuming that the triangle BMC is isosceles, then what unit of mathematical knowledge that may be useful to us in the construction of the forward flow of causality proof can be extracted from that information? Well, according to Euclid's Book 1, Proposition 5, the famous Pons Esinorum, if a planar Euclidean triangle such as BMC is isosceles, then the magnitudes of the angles at the base of the triangle must be equal one another. In other words, the magnitude of this angle, let us write it down as the angle CBM. The angle CBM must be equal to the magnitude of the angle, this guy, BCM. Angle BCM. Again, in the previous episodes, we agreed to model our implications with geometric points. Consequently, let's write it down that from what is given, from the fact that the triangle BMC is isosceles, we managed to put together an implication this way, which we will call Book 1, Proposition 5. Very well, now that we know that the magnitudes of the interior angles at the base of the triangle BMC, by assumption, equal one another, then what next unit of mathematical knowledge can we deduce from that information and find it tactically useful? Well, following the immortal advice of the immortal author George Poya from his immortal book, How to Solve It, have you used all the data? And at this point, we did not use all the data because, for example, we haven't made any use of the fact that we're given a trapezoid. And what is a trapezoid? We'll take it that a trapezoid is a convex quadrilateral that has two opposite sides parallel and two other opposite sides not parallel. In this case, the sides BC and AD are parallel, and the straight line BM can play the role of what? The straight line BM can play the role of a straight line that is falling on two parallel straight lines, the straight line BC and AD, and according again to the same Euclid's Elements, Book 1, Proposition 29, if that is the case, if a straight line is falling in two parallel straight lines, then that straight line makes the magnitudes of the alternating angles equal one another. In other words, in this case, the angle, for example, CBM by magnitude must be equal to the magnitude of this angle, BMA. So the angle CBM, these two guys, we keep writing it down, must be equal to the angle of magnitude of the angle BMA. Angle BMA. Very well. This angle and this angle must be equal. So by, let's say, we'll depict this proposition, Book 1, Proposition 29, as another point in our reverse order reasoning. Now, what other tactical useful unit of mathematical knowledge can we derive from the fact that the magnitudes, for example, of these two angles are equal? Again, have we used all the data? So far we haven't, because we haven't made use of the, for example, circle S1. Let us analyze the magnitude of the angle BMA. We see that the angle BMA is the angle in the circle S, because the vertex of that angle M resides precisely on the circle S1, subtends the arc BA, this arc right here, and at the same time, that very same arc is subtended by what angle? Looking carefully at the diagram presented, we see that the arc BA right here is subtended by the angle BOA, this angle right here, BOA. And by Euclid's elements, this time book 3, where Euclid lays out the theory of circles, proposition 21, we know that in this case, the angles in the same segment equal one another. In other words, the magnitude of the angle BMA must be exactly the same as the magnitude of the angle BOA. So here we write it down, equals the magnitude of the angle BOA. Again, the angle BMA subtends the arc BA, which is the same arc that is subtended by the angle BOA, and by Euclid's book 3, proposition 21, the magnitudes of these angles must be equal one another. Now we can repeat pretty much the same reasoning almost verbatim, but for the remaining angle. For example, the straight line CM in this case falls on two parallel straight lines BC and AD, and by the same book 1 proposition 29, that straight line makes the magnitudes of the alternate angles equal, which means that in this case the magnitude of the angle BCM must be equal to the magnitude of this angle CMD. So we'll write it down over here, magnitude of CMD. And analyzing the angle CMD, we see that the vertex of that angle belongs to the circle S1, but it also belongs to the circle S2. And in the circle S2, the angle CMD subtends the arc CD, which is exactly the same arc that is subtended by which angle? By this angle right here, COD. And again, by the same book 3 proposition 21, the magnitudes of this angle must be equal one another. So here we write down the fact that that angle CMD by magnitude must be equal to the magnitude of the angle COD. Angle COD. Excellent. Now, what do we see? We see that the angles BOA and COD form what type of relationship? Well, we're given that the straight lines AC and BD intersect precisely at the point O, and by Euclid's book 1 proposition 15, this time book 1 proposition 15, what does it say? Euclid's Elements book 1 proposition 15 says that if two straight lines intersect each other, then they form actually two pairs of so-called vertical angles, the magnitudes of which pairwise equal one another. In other words, the straight line AC and the straight line BD intersect in such a way that they form two pairs of vertical angles, the vertical angle BOC and AOD, but in this case they are of no interest to us, and a pair of vertical angles BOA and COD. So indeed, we show that by assuming that the triangle BMC is isosceles with the corresponding lengths of the sides equal one another, we arrived at certain amount of material that was given to us. And we can say that represent this is what is given. Let's say write it down here. This is given. This is what sought after, this material. So by reasoning in reverse order, by starting from what is sought after and working our way towards some material that was given at the problem, we managed to arrive at that material. And now on the reverse order journey, we this time did manage to collect enough of useful and tactically advantageous material. So now we can use these propositions as our landmarks and construct the traditional forward flow of causality reasoning that is sought after. For example, if you are studying Euclidean geometry in middle school or high school, or maybe you're taking a Euclidean geometry course in your first semester, first year in college, and your math teacher or math professor gave you this problem as a homework assignment, you came back to class and your professor or teacher called you to the blackboard to explain how you solve this problem and share your solution with the class, you will traditionally begin your proof not with this reverse order reasoning, because unless unfortunately you attended a highly specialized physics mathematical school where precisely this material is the interest, you will begin your solution or your proof with the following statement. Consider the intersecting diagonals AC and BD of a given trapezoid. We know that by Book 1, Proposition 15, this intersecting diagonals form two pairs of vertical angles, of which of interest to us are only the angles BOA and COD, and by Book 1, Proposition 15, the magnitudes of this angle equal one another. So we'll write down, for example, BOC and COD, let's say, is the angle alpha. So we mark it on our diagram, angle alpha, and this one will be angle alpha. We also, in your presentation, you will not have this at the moment, and you will not have these angles marked. You will only have the angles BOA and COD marked as alpha. Then, from that implication, you will then present your idea by using the circles. The angle BOA, for example, subtends the arc BA, which is also subtended by the angle BMA. And at that point, you will state that by Book 3, Proposition 21, the magnitudes of these angles equal one another. So the magnitude of the angle BOA must be the same as the magnitude of the angle BMA. Here you will mark this angle, you will put alpha over here, and you will repeat pretty much this idea for the angles in the circle S2. You will say that since the angle COD subtends the arc CD, which is also subtended by the angle CMD, by the same Book 3, Proposition 21, the magnitudes of this angle equal one another. You will mark this angle, you will put alpha over here, and you will set things up for the next step, because you showed that these two angles are equal, and these angles also use the straight line DA for their corresponding sides. We know that the straight line CM and the straight line BM, they both fall on two parallel straight lines, the straight line BC and the straight line AD. And here, by book 1 proposition 29, you will claim that the magnitude of the angle CMD must be equal to the magnitude of the angle, BCM. This angle, you will mark it alpha. And by the same book 1 proposition 29, you will claim that the magnitude of the angle BMA is equal to the magnitude of the angle, for example, MBC or CBM. You will mark that angle. You will put the angle alpha here as well. Here you will have to be careful. Here you can no longer use book 1 proposition 5, the famous Pons Asinorum, but you can use here book 1 proposition 6. So your forward flow of causality will be from what is given. Then you will invoke book 1 proposition 15. Book 1 proposition 15, the proposition that connects, says something interesting about the magnitudes of the vertical angles. Book 1 proposition 15 here. Then from book 1 proposition 15, you will use the angles in the same segment. So here you will come to book 3 proposition 21, like so. Then you will invoke the theorem that says something interesting about the angles that are formed by a straight line falling on two parallel straight lines. This will be book 1 proposition 29. And carefully, on your last step, you will have to use book 1 proposition 6 this time. Let's say from here we'll jump to book 1 proposition 6, which is the converse of book 1 proposition 5. And that theorem claims that if the magnitudes of the interior angles at the base of a given planar Euclidean triangle equal one another, which is the case in this scenario, since we proved that the magnitudes of the angles CBM and BCM equal one another, then the corresponding triangle is isosceles with the lengths of the sides that lie opposite equal angles being equal. And from here we conclude that triangle BMC is indeed isosceles. So as I mentioned before, in season 1 episode 3 and season 2 episode 3 and season 2 episode 4, where I explained how the heuristic flavor of the reverse order problem solving approach works, the idea about chaining if P then Q implications in reverse order may have been a little bit too abstract. Hopefully with this example we made it very concrete, very tangible, and now we see that the implications that we generate for the forward flow of causality may be different. In this case, our last implications are different. In reverse order, the implication was book 1 proposition 5, but in the forward flow of causality we had to use book 1 proposition 6. But overall, this is how the heuristic flavor of the reverse order problem solving approach can be applied to the solution of the problem S2M8. That solution is complete, and now we will move on to the solution of the problem S2M9. Excellent. We just solved the problem S2M8 using the heuristic flavor of the reverse order problem solving approach. And in the problem S2M9, we will also try to apply the heuristic flavor of the reverse order problem solving approach to the process of searching for a solution of the problem in which we're given two coplanar circles, the circle S1 and the circle S2, in their general position for this specific problem, which means that the circle, let's say S1, has the radius, which is radius, let's say R1, that is strictly larger than the length of the radius R2. These circles do not intersect. The smaller circle S2 is not contained by the larger circle S1. And under these conditions, if we're also given precisely the positions of the centers of the circles S1 and S2, in other words, given the positions of the points O1, which is the center of the circle S1, and given the position of the point O2, which is the center of the circle S2, we're asked to construct, invent, synthesize, discover at least one algorithm according to which the external and the internal tangents to two such circles can be constructed. As a reminder, a tangent to two circles in their general position is a straight line that has precisely one point in common with the circle S1 and the circle S2, and such a straight line intersects the line of centers, or the straight line that passes through the centers of the two given circles, outside of the line segment O1, O2, and we designate the external tangent with the symbols tau sub x, where x stands for external tangent. Internal tangent, on the other hand, is also a straight line that has precisely one point in common with the circle S2 and precisely one point in common with the circle S1, but both of such internal tangents intersect the straight line of centers, or the straight line that passes through the points O1 and O2, precisely in between the points O1 or O2, and two such internal tangents are shown here. We designate one with the symbols tau sub n, where n will stand for internal. Now, the process of searching for an algorithm, a mathematical algorithm, or a finite description of a finite number of steps, each of which involves the use of only the Euclidean compass and the Euclidean straight edge, can be done in a number of various ways. Here, because right now we're studying the mechanics of the reverse order problem solving approach, we will try to synthesize, construct, invent, discover that algorithm using precisely the heuristic flavor of the reverse order problem solving approach. And from the previous episodes, we know that in general, the basic problem solving approaches that we're studying initially on this channel are a sort of heuristic templates, which are described with plain, everyday, almost spoken English without any highly technical and highly specific mathematical jargon. And they present themselves to us as a coin with two sides. The heuristic template with no algorithmic guidance on the one side, and on the other side, these heuristic templates or problem-solving approaches present exactly the fact that mathematics is an art of telling a story of how and why. As authors of such a story, we need to exercise our creativity, ingenuity, and improvisational skills in order to put that story together. As such, given the material in this problem, again, we, as the heuristic flavor of the reverse order problem solving approach prescribes, we're looking for at least one algorithm that will allow us to construct, for example, just one external tangent to two given circles in their general position, because if we know how to construct one external tangent, we know how to construct the other. And we're looking for a similar algorithm to construct at least one internal tangent to two circles in the general position, since if we know how to construct one internal tangent, we know how to construct the other. For that purpose, we will, again, for demonstration purposes, we will apply the heuristic flavor of the reverse order problem solving approach, and temporarily we will take it that, let's say, the mathematical oracle somehow did something, and with the finite in a finite number of steps, using the Euclidean compass and the straight edge alone, the mathematical oracle did something and said, here, an external tangent and an internal tangent to two circles in the general position are given to you, ready, set, go. Taking, for example, the existence of an external tangent to two given circles as our initial assumptions, as our initial assumption, what type of tactically useful unit of mathematical knowledge can be derived from that assumption? Again, this problem seems to be very difficult because not only we have to construct a straight line that is tangent to a circle, we have to construct a straight line that is tangent to two circles at the same time. So maybe we will begin the search for a solution of this problem with just a tangent to one circle. What type of theoretical, for example, material comes to mind when we look at a given tangent to one circle? Well, in this case, Euclid's Elements, Book 3, Proposition 18 comes to mind. And according to this proposition, if a straight line, let's say straight line, touches a given circle, this will be, for example, a tangent to a circle, then Euclid in Book 3, Proposition 18 proves that if a straight line is drawn from the center of the circle S, for example, from O, onto the shared point between the circle and the tangent, let's call that point T for tangent, then the straight line OT here and the given tangent will be what? Then the straight line OT and the tangent tau will be precisely perpendicular, or the straight line OT will be perpendicular to the tangent tau. Carrying this information from the book, so to speak, into our problem, what kind of tactically useful observation can we make? Well, if one external tangent to two given circles in their general position is given, that means what? The straight line drawn from the center of the circle S1 from the point O onto this given external tangent tau x must be perpendicular to it. Let's call this point, for example, T1. In other words, the straight line O1 T1 will be perpendicular to the given external tangent tau x. And since that external tangent is also tangent to the circle S2, the same idea must apply. So a straight line drawn from the center O2 of the circle S2 to the shared point, let's name the point T2, like so, must be perpendicular to the given external tangent tau x. Now that we have this much information that we put into the given problem, what tactically useful observation can be made. Here's the thing. Different people looking at the same problem will see different things. And even though I mentioned many times, and I will mention it many more times, my personality on this channel is irrelevant, but even sometimes when I look at one and the same problem at different times, I can see different things. In this case, what I see is, for example, what I see is a wonderful geometric transformation known as parallel translation. Now, parallel translation is carried out along a certain vector. So the question here, what type of vector can we use for the parallel translation of the ambient Euclidean plane that contains the circles S1 and S2? Well, as I mentioned before, sometimes, now and then, here and there, I dabble in woodworking. So here's my trusty circular saw cutting guide, which plays the role and an incredible simulation of a Euclidean straight edge or an unmarked ruler. So what I see, for example, combinatorially, again, which points can we work with? Well, we're given uncountably many points that make up the circle S1. We're also given uncountably infinitely many points that make up the circle S2. Right now we have the point T1, that is the point that is shared by an external tangent tau x and a circle at S1. The point T2, which is a shared point between the external tangent tau x and the circle S2, and we're also given two centers of the circles S1 and S2, the points O1 and O2 correspondingly. That is technically plenty of material to work with, but the points O1 and O2 here represent the low-hanging fruit. So an idea that comes to mind when we try to generate an algorithm requested is the vector T2O2, this guy, and the vector T1O1. So the parallel translation of the plane can be carried out along the vector T1O1, or it can be carried out along the vector T2O2. Here we execute the following maneuver. We split the ambient Euclidean plane into two copies. One copy is an opaque background plane that contains all the materials that we have, all the material that we have so far. And the second or top plane that is transparent, and it only contains the external tangent tau x. Now, when we translate the plane along the vector T2O2 this way, what will result? Remember, the opaque background plane that contains all the material in this problem remains stationary or fixed. The only object that in this case is really translated in our model is the top or foreground transparent layer. And an interesting feature of parallel translation is that under non-trivial, along the non-trivial vector or non-zero vector, each and every point of the plane undergoes that transformation. In other words, under every non-trivial parallel translation, there are no fixed or stationary points. That means that every point that makes up the external tangent tau x will be translated by the corresponding amount, and the result of that translation will be, again, a straight line that will be parallel to, let's, for example, try to parallel translate this straight line this way, for example, somehow. I'll show it in dashed line just to show that this is a result of parallel translation. We will call that straight line, let's say, we'll call it tau prime x. And as a result of this parallel translation, the given external tangent tau x will be taken into a straight line tau prime x that passes through the point O2 and is parallel to the straight line tau x. Again, combinatorially, on your own, you guys are encouraged to carry out the parallel translation of the plane along the vector T1, O2 and see and try to figure out what happens if we translate our given external tangent into a straight line that passes through the point O1. Right now, for demonstration purposes, we will only analyze the case when our helper tangent tau prime x passes through the point O2. Now, what type of tactically useful information can be extracted from that maneuver? Well, due to the mechanics of the geometric transformation known as parallel translation, we know that, for example, when the straight line tau prime x will intersect the straight line T1, O1, let's name that point right here. What should we name it? We should name it probably, because this length is R2, this length is R1, so we'll name that point R2 suggestively, uppercase R2. The shape R2, T1, T2, O2 will be what? That shape will be a rectangle because we have a straight line, for example, T1, O1, falling again on two parallel straight lines, making the alternate angles equal, and in this case these angles are right. Likewise over here, this angle between the straight line T2, O2 and the straight line tau prime x will be right. Consequently, the shape T1, T2, O2, R2 will be a rectangle. And what does that mean? That means that the length of the line segment T1, T2 will be equal to the length of the line segment R2, O2. And that also means that the length of the line segment T2, O2 or O2, T2 must be equal to what? In length? To the length of the line segment R2, T2. In other words, this length right here will be what? The length of the radius R2. Let's write it down over here, for example, right here. So the length of the line segment T1, R2 must be equal to the length of the radius R2. That maneuver should be transparent and understood by everyone. Again, as a quick recap, we used the theoretical information given to us by Book 3, Proposition 18, and the observation that a straight line through the center of the circle to the point of tangency of that circle with a straight line will be perpendicular to that line. We reflected this fact by two circles at the same time. We executed parallel translation of the ambient Euclidean plane along the vector T2, O2. We obtained a rectangle as a result, and the length of the sides, of the opposite sides of that rectangle must be one and the same. The length of the line segment T1, R2 must be equal to the length of the radius R2. And now comes the key observation. If the length of the line segment T1, O is R1, then what can be said about the length of the line segment R2, let's write it down here, R2O1. What is the length? What tactically useful information can be extracted from the knowledge of the length of the line segment R2O1? Well, in this case, it is evident that the length of this line segment will be the delta. Let's mark it like so, delta, and it will be equal to the difference between the lengths of the radius R1 and the length of the radius R2. The difference between the length of the radius R1 and the length of the radius R2. And it is known, we know, or there exists an algorithm that in a finite number of steps with nothing but a Euclidean compass and a Euclidean straight edge constructs geometrically the equivalent of the difference of two line segments. However, what can be now said about the angle O1 R2 O2, for example? Still, the straight line, the helper straight line tau prime x is what? As we showed earlier, is perpendicular to the straight line O1 T1. That means the angle over here, the angle, let's write it down over here, the angle O1, O1 R2 O2 is right. Pi over 2 radians, this angle is right. So now, what do we have? We have a helper straight line tau prime x that passes through the point, given point O2, and is orthogonal or perpendicular to the straight line O1 T1. What type of tactically useful and relevant information in this case can be extracted from that knowledge, from that information? Well, it should be evident that in this case, the straight line tau prime x, which we obtained as a result of the parallel translation of the plane, can play the role of a tangent straight line to the circle that is centered at the point O1 and that has the difference delta R1 minus R2 as its radius. We'll name that circle as delta, like so, delta. And in some sense, I really do not want to overload our discussion with too much technical information, but what we have here in this, guys, is another extremely useful and powerful problem-solving approach that we will discuss in the future. But for now, I'll mention to you guys, this method is called reduce and conquer, which means that a difficult-to-solve problem sometimes, somehow can be massaged into or reduced to a previously solved problem. In this case, what is a previously solved problem? Well, with the Euclidean compass and the straight edge alone in a finite number of steps, it is very well known how to construct a straight line that is tangent to a given circle, such as the circle delta, and that tangent passes through a given point, such as a point O2, located, of course, outside of the given circle, and in this case, the point O2 is certainly outside the circle delta. As a matter of fact, maybe in the future I'll make an episode dedicated to it, but there exist at least, or I know at least of 5 distinct ways to construct a tangent to a given circle through a point outside of that circle, and that problem can be solved in a number of different ways, based, for example, on the theory of parallel straight lines, or not based on the theory of parallel straight lines. And another construction or type of constructions can be based, for example, on whether the point of tangency is explicitly constructed or not, but we will leave this discussion for later time. For now, we will use perhaps one of the uh, more popular ways to construct a tangent to a given circle through a point outside of that circle. And we know how to do it by using the so-called Thales theorem. In other words, if we bisect the line segment O1, O2 with a perpendicular bisector, locate the point where that bisector intersects the line segment O1, O2, use that point as a center, or use the line segment O1, O2 as a diameter of a circle that will intersect the circle delta at 2 points, and one of such points will be enough for us because the corresponding angle, will be precisely right angle by the Thales theorem. At this point, our use of the heuristic flavor of the reverse order problem solving approach for a given problem is over. By reasoning in reverse order, or by taking what is sought after, one external tangent to two circles in general position as given to us, we managed to collect enough of tactically useful information, and now we abandon that flow of reverse order and we construct a forward flow of causality solution, which we explain as, or which we describe as follows. Given two circles in their general position, I'll mark it over here schematically. Let's say we're given one circle, the circle S1, its center point O1, given another circle S2 with the point O2. We know that radius R1 is strictly larger than the length of the radius R2 of the circle S2. Again, for optimization purposes, because we will evidently need the straight line of centers, first we construct a straight line of centers O1, O2, and we name that straight line as L as the first step. Then we need to construct the circle named delta that is centered at the point O1 and that has the difference of the lengths of the radius R1 and R2 as its radius. How can this be done? Well, the straight line L will intersect the circle S1 at 2 points. For practical reasons, we pick this point that sits on the other side of the center. Here we will draw the circle S2. Here we will draw the circle S2. Circle S prime 2, which is basically a circle that has the same radius as the circle S2. That circle will intersect again the straight line L at two distinct points, and in this case, which point we will pick? In this case, we will pick the point that is located inside of the circle S1, because this difference, and we will call that point, for example, R2, and then this distance right here will be precisely the delta, or the difference between the lengths of the given radii R1 and R2. Then we will, again, with the compass, we construct the delta. Let me use maybe red chalk to designate this guy. We construct the helper circle delta that is centered at the point O1. The circle will be called delta, and it has the radius, which is by length, the difference between the lengths of the radii R1 and R2. And now, what do? Now we bisect the line segment O1, O2. Let me see, somewhere like this. we bisect that line segment like this. With the bisector B, will intersect the straight line L at the point, let's say O, we'll call it O, this point O. Then we construct on the diameter or line segment O1, O2 as a diameter. We construct the circle, the helper circle S, the circle S, for example, the helper circle S. That helper circle S will intersect our delta circle at 2 points. Here, the point, for example, A, and here will be the point B, this point right here. And what final step do we carry out here? Well, we technically do not need to construct the tangent to the circle delta through the points A and O2. All we have to do here, remember, we have to, in reverse, like reversing the reverse order reasoning, we get our forward flow reasoning. So all we have to do is construct the straight line O1, R2 and extend it until we obtain the point T1. So here we will draw the straight line O1, O2 like so. And for the second tangent, obviously, O1B like so. That straight line will intersect the circle S1 at 2 points, but we pick, for example, this one, this point. And as a final step, what do? Again, with the Euclidean compass and the straight edge, we construct a straight line that is perpendicular to this straight line O1A and passes through the point A. And we know that such a straight line will be precisely perpendicular to that straight line O1A. It will be tangent to the circle S1, and through the magic of parallel translation, we know that that straight line will also be perpendicular to the straight line constructed through the center O2 of the circle S2 and the point of tangency here T2. And such a straight line will be an external tangent sought after. And if we repeat the same steps for the straight line that passes through the point O1 and B, here somewhere will be the other point of tangency and the straight line. The second external tangent will be constructed. Now that we solved the problem for external tangents, we can address the search for an algorithm for the construction of the internal tangents, which is coming up next. Now that we solved the problem with constructing external tangents, we of course gained a lot of useful insight into this problem. And as we address the problem of inventing, discovering, or synthesizing an algorithm for the construction of the internal tangents in a finite number of steps using the Euclidean tools alone, the Euclidean compass and the Euclidean straight edge, we already see that we can reuse the same idea of the wonderful geometric transformation known as parallel translation, except that in this time, again, we will use the theoretical knowledge baked into the Euclid's Elements Book 3, Proposition 18, which says that if a straight line touches a circle, then the straight line through the center to the point of tangency must be perpendicular to that tangent. That means that the straight line O2, let's name this point again T2 here, must be perpendicular. The straight line O2, T2 is perpendicular to the internal tangent tau n. And the, let me take yellow color here, straight line O1, T1, this way, constructed this way. Let's name that point T2, T1, I'm sorry, T1. Then the straight line from the center of the circle S1 to the point of tangency with the internal tangent tau n must be perpendicular to that tangent. And again, we remember the difference between the external tangents and internal tangents is the following. External tangents to two circles in their general position intersect the line of centers outside the line segment O1, O2, and the two internal tangents to two circles in their general position intersect the line of segments, the line of centers, I'm sorry, precisely inside or in between the points O1 and O2 is shown over here. Again, once we have the line segments O1, T1, or the straight line O1, T1, and the line segments O2, T2, or the straight line O2, T2 in place, then stepping back from the problem, as the German mathematician Karl Gauss used to say, and hoping that the solution to the problem will emerge and stare at us, what do we see? Again, we see, for example, that again, if we split the given plane into two copies, the opaque background copy that contains all the material in the problem, and the second foreground copy, or the foreground transparent plane that only contains, for example, this internal tangent tau n, that again, we're given uncountably infinitely many points that make up the circle S1. We're given uncountably infinitely many points that make up the circle S2. We're also synthesized the points T2 and T1. We're also given the points O1 and O2, which are the centers of the given circles of the circle S1 and S2 correspondingly. And in this case, the given centers O1 and O2 are the low-hanging fruit. We can carry out the geometric transformation of parallel translation along the vectors, for example, T1, O1, or along the vector T2, O2. As an informal homework assignment to the eager students of mathematics, we will leave the analysis of the case when the parallel translation is done along the vector T1, O1 as an exercise. You guys should see what kind of solution or what kind of algorithm unfolds if we parallel translate the plane along the vector T1, O1. Here we will analyze in public the algorithm that will result if we parallel translate the given plane along the vector T2, O2 this way. Again, we know that under every non-trivial parallel translation, there are no stationary or fixed points. Each and every point undergoes a non-trivial transformation, and under parallel translation, a point is taken as to a point, a straight line is taken into a straight line, a circle is taken into a circle. So in this case, the parallel translation of the foreground transparent plane along the vector T2, O2 will result in, let's say, let me show it with a dashed line. Will result in a straight line that we will name it T prime n. Tau prime n, that is parallel to one of the given internal tangents tau n. And again, using the heuristic flavor of the reverse order problem solving approach, that is what we do. Instead of trying to fight the forward fight, so to speak, and trying to construct a traditional and requested and sought after forward flow of causality reasoning, we temporarily suspend that effort, and in order to gain insight into the process of discovering the sought after algorithm, we take what is sought after, the one of the internal tangents tau n, as a given, we try to reason our way backwards to some material that is given. In the previous case, we saw that we reasoned backwards into the material that was given, the lengths of the radii R1 and R2, and we boiled down that problem to the difference for the external tangents. Remember, there was a difference, delta, we designated R1 minus R2. And in this case, we take that the mathematical oracle looked at the two given circles and their general position, did something wonderful with the Euclidean tools and said, here, you have one internal tangent to two circles, ready, set, go. We said, wonderful, we'll take this as an input for our reasoning, and trying to reason in reverse order, we saturated our problem with the points T1 and T2. Here, naturally, so to speak, popped out the vector T2, O2. Along that vector, we translated the ambient plane. We obtained a straight line tau prime n, which is parallel to the given internal tangent tau n. And what do we see now? What kind of tactically useful information can be extracted from that maneuver? Well, again, if we extend straight line O1 T1 like so, what will happen? That straight line will be perpendicular to the helper straight line tau prime n, and these two straight lines will intersect, let's say again, at a point that we will name suggestively as R sub 2. R sub 2. Again, the shape O2, T2, T1, R2 will be what? That shape will be a rectangle with the length of the opposite sides being equal one another. The length R2, O2 equals to the length of the line segment T1, T2, and likewise the length of the line segment O2, T2 must be equal to the length of the line segment R2, T1, but that length precisely represents what? The length of the radius R2, and the length of the line segment O1 T1 represents what? The length of the line segment O1 T1 represents the length of the radius R1. And what is the length of the line segment O1 R2 as we captured over here in the previous case? Well, it should be evident that the length of the line segment O1 R2 this time is this sum. So instead of delta, in this case, we will say that our length is this sum, sigma, and then here we will use the plus sign instead of plus sign R1 plus R2. Even though that the length of the line segment T1 R2, note carefully, wonderfully, still the length of the radius R2. What further tactically useful unit of mathematical knowledge can be extracted from that fact? Well, we know that due to the mechanics of the geometric transformation of parallel translation, the straight line tau prime n will be what? Perpendicular still to the straight line O1 T1 at a point R2, and that helper straight line tau prime 1 can double up as what? That straight line tau prime n can play the role of a tangent to this circle. Let me draw it in this green color. I'll draw it partially here. Circle that we will name, for example, circle through 1 to R2. We will name it sigma, like so. Sigma for the sum, circle sigma. And the straight line again, tau prime n, will pass through the given point O2, and it will be tangent to the helper circle sigma that is centered at the given point O1 and has for the length of its radius the sum of the lengths of the radii R1 and R2. And first of all, we know how to construct a geometric representation of the sum of two line segments with Euclidean tools in a finite number of steps with the Euclidean compass and the Euclidean straight edge. And that miniature problem also represents a previously solved problem. There are many ways to construct a tangent to a circle through a point outside of that circle. We will use one of the more popular constructions that is based on the Thales theorem. And at that point, notice carefully that in our reverse order, recall our previous discussions, chain of implications, we arrived at some material that is given. What is that some given material? Well, we're given the length of the radius R1, we're given the length of the radius R2. Consequently, we know how to construct a line segment that is a geometric representation of the arithmetic sum of the lengths of these line segments with Euclidean tools alone in a finite number of steps. And that observation, since we arrived to a material that is given, terminates our reverse order attempt or an attempt to solve the problem in reverse order. And at this point, we can abandon that work and thank the heuristic flavor of the reverse order approach and put together a sought after or traditional forward flow of causality algorithm. And that algorithm will look as follows. Again, given, let me use these colors. Given the circle, I'll draw this schematically. Given circle S1 and its center O1, circle S1 and the center O1, given the circle S2 and the point O2, in order to construct one internal tangent to these two circles, we again construct a straight line of centers. We name this straight line L, for example. That straight line L will intersect the given circle S1, for example, at two distinct points. Practically, again, we may choose, for example, the further point, the point that is located on the other side of the given center O2. Here we'll construct a helper circle S'2, this circle right here, which is a circle centered at that point and has R2, or the radius of the second circle S2. That circle S'2 will intersect the straight line L at two distinct points. And in this case, which point do we pick? Correct. Last time for the external tangent, we picked the point that was located inside of the circle S1. But this time, in order to generate the requested, the needed sum, R1 plus R2, we'll take the point that is located outside of the circle S1. We'll give that point a suggestive name, for example, R2. Now the distance O1, R2 will be what? It will be the sigma, the sum. We construct then, I used yellow, let me use red one. We construct the helper circle sigma, that is centered at the point O. Let's say sigma centered at the point O1 with the radius equal to R1 plus R2. For example, in this notation, we can say that sigma is a circle that has the center, the point O1, and the radius R1 plus R2, the sum. And now all we have to do is construct a tangent or go through the steps that lead up to the construction of the tangent to the helper circle sigma 1 through the point O2, and already we know how to do it. In the previous segment, we explained one out of many different ways to do so. Again, we bisect the line segment O1, O2. Let me see, somewhere here maybe, like so. We bisect the line segment O1, O2 with the straight line B. The point where the bisector B intersects the line of centers L will be named, for example, O, using O as a center and the line segments O, O1, O, O2 as a radii. We construct a helper circle. Let's see, we construct the helper circle schematically. We'll call it the circle S. We construct the circle S centered at the point O, and it has the radius O, O2, O, O1. That circle S will intersect the circle sigma at 2 points. Let's say at the point A and at the points B. 2 points, 2 distinct points. And again, for the purposes of optimization, remember in our season 1 episode 3, when we're discussing various mathematical algorithms, we want to make sure that our algorithm is as short as possible or takes the smallest number of steps. So in order to optimize our construction, we don't really have to draw the external tangent through the point A and the point O2. We know through our reverse order reasoning that will be the case. All we have to do here is construct the straight line O1, R2, the equivalent of, so that that straight line will intersect the given circle S1 and thus reveal the point of tangency between the tangent sought after and the circle S1 and S2. Consequently, here as a separate step, we construct the straight line O1, O1, OA, O1A, and we construct, if we want to, for the second tangent, the straight line through the points O1 and B, like so. Here, the straight line O1A will intersect the circle S1 at this point right here. We'll call the point T1. And the perpendicular line, straight line perpendicular to the straight line O1A through the point A, like so, will be, again, I apologize for a schematic, not very precise drawings here, but the idea is that a straight line through the point A perpendicular to the straight line O1A, like so, will be precisely the internal, one of the internal tangents sought after. And again, the straight line O1B will intersect the circle S1 at 2 distinct points. We will need only one, this one, and then a straight line that is perpendicular to the straight line O1B and passes through the point B will be the second internal tangent sought after. And as expected, these two internal tangents will intersect at a point that is located precisely in between the centers O1 and O2, and the problem is solved. This is only one way to solve the problem. Those of you who think that this is enough can skip the next segment and go to the next problem. This will be our first computer science problem. But for curious travelers, in the next segment, we will present a second algorithm for the construction of the internal and external tangent that is different from the way that we explained it over here. But again, as a quick recap, in order to construct the algorithm that we presented here, that is a traditional forward flow of causality algorithm that starts with what is given, 2 circles and 2 centers, and then describes the steps, describes a finite number of steps that can be taken with the Euclidean tools alone, with the Euclidean compass and the Euclidean straight edge, the steps that lead to the construction of the two internal tangents in this case. And in the next segment, we will present a solution that is based on a different geometric transformation. Before we look at the second solution of the mathematical problem S2M9, please allow me to remind you that the program that I declared in the banner of this channel, the development, the nurturing, and the exposition of the ability to think out of the box in mathematics, theoretical physics, and computer science, means that on this channel, we of course care about the answer to the problem, but we care much more about the process or the way in which that answer was obtained, which means that if, for example, someone gave us a solution to possibly very difficult mathematical problem, just stated out of the blue without any motivation, that we will not care that much about the solution, because for us, the first-class citizen is the process that led up to the generation or construction or discovery or invention of that solution. And in some sense, all the problem-solving approaches that we studied so far and the problem-solving approach that we're studying now precisely create that environment that allows us to construct and follow that process of a discovery or invention or a construction of a solution. And so far, I have been picking or designing problems in mathematics or computer science that expose or allow us to study or concentrate just on one specific problem-solving approach, but in reality, less toyish and more realistic or more serious, more grown-up problems usually solved when several problem-solving approaches are strung together in a specific combination or in a specific permutation. In the solution of the problem S2M9 that we discussed in the previous two segments, we should really look at this solution, and if we analyze it, then we will realize that while solving that problem, we started with the reverse order problem solving approach. Then we actually used transform and conquer problem solving approach when we executed the parallel translation of the plane. And then we also used another problem solving approach that I haven't discussed yet, reduce and conquer, which means that the process of generation of the solution of the problem S2M9 involved actually the reverse order problem solving approach plus reverse order plus transform and conquer problem solving approach plus reduce and conquer problem solving approach. So if, for example, we associate each one or each single problem solving approach with a musical note, then in reality, or with more serious, with more grown-up problems, we actually we do not play one note at a time, but we play several notes at a time, and we take a musical chord when we construct a solution of the problem. And again, in the previous two segments, what really transpired is a combination of the reverse order, transform and conquer, and reduce and conquer problem solving approaches. Now let us come back to the second or to another distinct solution of the problem S2M9. We're given two circles in the same plane in their general position, meaning in the position when all four shared tangents to these circles can be constructed, two external tangents and two internal tangents, and we're asked to generate an algorithm for the construction of the external and internal tangents. In the previous two segments, we used the geometric transformation of parallel translation, and for the algorithm for constructing external tangents, we use the delta, the difference between the length of the radii of the given circle, and for the algorithm which allows us to construct the internal tangents, we use the sigma, or the sum of the lengths of the given radii of the circles. Again, in real time, when we solve a problem, sometimes it so happens that probably a lot of students just walk away from the problem and look for another problem to solve. But in reality, it pays to loiter around the solved problem, and it really should be an integral part that is weaved into the overall fabric and the culture of studying mathematics. And that idea, or that culture, amounts to fixing a given problem and trying to invent as many as possible different solutions to this problem. As such, when we look at this problem with a different set of eyes, what other algorithm can be invented or discovered in this case that is based not on the idea of parallel translation? Well, in this case, we again, in real time, we try and fail several times, but a happy thought may occur to us that another wonderful geometric transformation known as homothety of the plane, or the homothety of the space in general case, may also be used in order to generate a different algorithm for the construction of the external and internal tangents to two given circles. For those of you who do know how homothety works, you may skip to the section where we will discuss the actual solution. If you do not know how the geometric transformation of homothety works, then you have a little bit of work cut out for you. You should really try to study that transformation out of band. Elsewhere, here in the lightning round, I will say that the homothety of the plane, for example, is such a transformation that takes, for example, a point P in a given plane into a point P prime, such that all 3 points O, P, and P prime are collinear, belong to one and the same straight line, and the distance, for example, OP prime equals to K times the distance from the point O to P, where K is a real number. In this case, that number will be, for example, can be greater than 1, or it can be greater than 0 and less than 1. And essentially, the geometric transformation of homothety of the plane means either a uniform expansion of the plane when the coefficient of homothety is a strictly positive real number that is greater than 1. If the coefficient of homothety is less than 1 but greater than 0, then the corresponding transformation amounts to uniform contraction of the plane. When the coefficient K, for example, is precisely 1, then this amounts to the identity transformation, and that identity transformation should not be overlooked, because once we have the or an identity transformation in a certain case, then it makes sense to analyze if that transformation or some type of it can form a algebraic structure known as a group. And in this case, things look good because we do have the identity transformation. And when the points P and its homothetical image P prime are located on the same side of the center of homothety O, that center of homothety is actually called external center of homothety, and we can designate it with the subscript X for external center of homothety. However, the coefficient of homothety can also be negative. And when the coefficient of homothety is negative, then the corresponding points, let me show it, for example, here. If this is the point P, then this is the point P, this is center of homothety O, it will be called internal, and then the homothetical image of the point P is the point P prime, such that the center of homothety is located in between the points P and P prime. In this case, the coefficient of homothety is less than 0 or negative, such as, for example, -2 or -3, and so on. And in this case, to that type of homothety with the negative coefficient, things work similar to the way they work in case of the homothety with the positive coefficient, okay, except that with the negative coefficient of homothety, the result of the transformation of the plane or of the space basically amounts to a commutative composition of the homothety with the positive coefficient and the transformation of central symmetry, or a central symmetry first, and the homothety of the plane or of the space with the uh, positive coefficient. Again, as a quick reminder, the geometric transformation of central symmetry basically means that any point in the plane, for example, P, is reflected in the center of the symmetry to the other side in such a way that the distance OP equals to the distance OP prime. This is basically how central symmetry works. And how is this information relevant to our problem? Well, it turns out that in their most general position, two external tangents to two given circles intersect with each other and intersect with the line of centers precisely at the point that plays the role of the external center of homothety. And the internal tangent to two circles intersect precisely at the point that plays the role of the internal center of homothety, or the center of homothety of the plane with the negative coefficient. That is why I gave these 2 points the suggestive names O sub x for the external center of homothety, as shown here, and O sub n for the internal center of homothety when the coefficient of homothety is negative. What does that mean, and how does this information apply to us, and where does the heuristic flavor of the reverse order problem solving approach comes in? Well, the heuristic flavor of the reverse order problem solving approach comes in again if we assume that the external tangents to two given circles are already given by the mathematical oracle. Then we know that the point where these external tangents intersect with each other and with the straight line of centers plays the role of the external center of homothety, and several features of the geometric transformation of homothety mean that a point under this transformation is taken into a point, a straight line is taken into a straight line, a circle is taken into a circle, and also, importantly for us, every straight line that passes through the center of homothety gets rebuilt point-wise, either expanded uniformly or contracted uniformly, but it still remains one and the same straight line. That means that, let's say, for example, we manage to somehow locate the center of the external center of homothety, and we work with, for example, with the smallest circle S2. What can we say in this case in respect with this transformation? Well, if we construct, and we know how to do it, a tangent straight line to the circle S2 through the point OX, then under the homothety with the coefficient that is equal to what? To the ratio, the length of the radius R1 to the length of the radius R2, the homothety of the plane will uniformly expand that plane, but as that expansion takes place, this straight line, this tangent to the circle S2 will remain what it is. It will remain tangent to the circle S2, but the circle S2 will uniformly grow and at some point become precisely the circle S1. The circle S1. Or equivalently, we can say that, for example, if we pick another coefficient, 1 over k, which will be precisely greater than 0 and less than 1, then we can construct a tangent, external tangent, or actually in this case just a tangent to the circle S1 through the point OX, and then the homothency of the parent plane centered at the point OX with the coefficient 1 over x will uniformly contract the plane and eventually bring the circle S1 into the circle S2, but importantly, the tangent will remain in this case one and the same. Likewise, if we somehow magically locate the point ON where the internal tangents intersect and execute the homothency of the plane with the negative coefficient over here, in this case, depending again, if we want to expand the plane, then it will be negative ratio R1 to R2, and if we want to contract the plane, it will be minus, we'll take with the reciprocal of this coefficient with the negative sign. But it is again important that for us it is enough to construct a tangent to any of these circles, to the circle S1 or the circle S2 through the point ON, and exactly precisely through the magic of homothency with respect to the internal center and with the respective negative coefficient, one tangent will also be the tangent to one of the circles will automatically become the tangent to the other circle. Again, notice how wonderfully the various problem-solving approaches work in tandem with each other. So in this case, we use the reverse order problem-solving approach. Again, we use transform and conquer problem-solving approach, where we transform, solve, or construct a tangent and then reverse transform. And we use the reduce and conquer problem-solving approach, which I didn't discuss yet, but I will discuss soon, in order to solve the problem of constructing a tangent to a given circle through a point outside of that circle. In the previous two segments, I already explained in detail how to construct the tangents to a given circle through a point not on that circle. I will not go into too many details. So now in this alternative algorithm, we're only interested in a geometric construction of the internal and of the external centers of homothency of two circles given in their general position, using the Euclidean tools, the Euclidean compass and the Euclidean straight edge in a finite number of steps. Well, that task again is also quite straightforward to carry out, and the way we can do it is as follows. We pick any point, for example, point P1, such as this one, the point P1, on a circle S1, for example. This point P1 can be picked anywhere on the circle S1, except that it should not be on the point that sits on the line of centers of two given circles. Then that step does not cost anything in our algorithmic work. We construct a straight line through the points P1 and O, like so, this way, this way. And then that can be done with a straight edge. With a straight edge and a compass, it is possible to construct a straight line that is parallel to the straight line P1, O1, but passes through the point O2, like so. And that second straight line, let's call it, for example, P, will intersect the second circle, the circle S2, at 2 points. Let's say call it point A and point B, for example. Doesn't matter. Now, it so happens that the center, the external center of homothety of these two circles in their common configuration, in their common juxtaposition, will be precisely located when the straight line of centers O1, O2 intersects with the 2 points that we obtained as explained above through through the construction of the parallel line and the straight line through the points P and A, supposed to precisely intersect the straight line of centers like so. In other words, as our forward flow of causality algorithm for the second solution, we construct the straight line of centers O1, O2, pick a point P1 on a circle S1 anywhere but the line of centers, construct a straight line through the points P1 and the center O1. With the straight edge and the compass, construct a straight line that is parallel to the straight line P1, O1 and passes through the point O2. That straight line will intersect that circle at 2 points. And if we pick the point where the helper parallel line P intersects the circle S2 on the same side as the point P1, then the straight line will intersect the line of centers precisely at the external center of homothety. And how do we locate the point that corresponds to the internal center of homothety? Exactly, all we have to do is pick the second point where the helper straight line P parallel to the straight line P1, O1 intersects the circle S2, or the point that is located on the other side of the line of centers with respect to the chosen point P1. So we pick that point, and all we have to do is connect the, let me use the red chalk in this case. Again, if we connect these 2 points, P1 and B, straight line through this point B and P1, that straight line will intersect the line of centers precisely at the point that plays the role of the internal center of homothety. Now, these 2 tasks of locating the external center and the internal center of homotheties again can be done with the Euclidean tools alone, with the Euclidean compass and the Euclidean straight edge in a finite number of steps. And once we locate these points as explained, we finish the construction of the tangents sought after in the same manner in which I explained that can be done in the previous 2 segments. For example, we bisect the line segment O2, OX, construct a circle, find the point where that circle that has O2 points, the line segment, O2, OX as a diameter, where that circle intersects the circle S2, and through these points it will be here and here. We precisely draw the straight line on top, the straight line on the bottom, and we thus obtain the external tangents. And likewise, we bisect the line segment, for example, pick which one you like, ON, O2 again, use the line segment ON, O2 as a diameter of a circle. That circle will intersect the circle S2 at 2 points, this point and this point, and that's how we construct the internal tangents through the point ON and one point of tangency and point ON and the second point of tangency, and thus the problem is solved. Again, as a quick summary, we assumed that the given problem has been solved somehow. We assume that the external tangents and the internal tangents to 2 circles in their general position are given. We try to work our way in reverse order and we made a number of tactically useful observations. That is, we noted that the external tangents to two circles intersect at the point that plays the role of the external center of homothety with a positive coefficient, and the internal tangents to two circles in their general position intersect at a point on the straight line of centers that plays the role of the internal center of homothety with a negative coefficient. And from these reverse order implications, we realize that the problem can be solved in a traditional forward flow of causality, and these are the steps that we explained previously, and this is it for the problem S2M9. And next we'll look at our first computer science challenge. Very well. In order to spice things up and bring in some variety into our work, here our next challenge will be computer science problem, not a strictly mathematical problem, because this is our first computer science problem. We'll designate it with season 2 CS1. You may recall that with the letter CS we designate the problems in computer science, with the letter M we designate the problems in mathematics, and with the letter P we designate the problems in physics. As such, in the problem S2CS1, our first computer science challenge, we're given a building that is 100 stories tall. The numbers, of course, go from the bottom: first floor, second floor, third floor, and so on, to the floor number 100. And we're given two eggs that are identical. They're visually indistinguishable, and they're identical in their break resistance. What does the break resistance mean? The break resistance means that if such an egg is thrown out of the building from any specific floor, it may break, as shown here, or may survive the fall and remain intact. And perhaps the whole idea of this exercise is to rank these eggs for their break resistance. And the challenge in this setup with two eggs and 100-story building is to find the smallest possible number and the respective testing scheme or the testing algorithm for the number of egg drops that will detect with absolute certainty the lowest floor, the fall from which either of these eggs will not survive. Again, one more time, the lowest floor, the fall from which the eggs will not survive, means the following. Let's say we start throwing these eggs from the first floor, the second floor, the third floor, and as we throw, these eggs do not break. They survive every fall from the floors number 1, 2, 3, and so on. But then all of a sudden, let's say, when we throw one of these eggs from, let's say, the 7th floor, the first egg, for example, breaks apart. Well, and if we throw another egg from any higher floor, from the floor number 8, 9, 10, and so on, the egg will also definitely break, because that's exactly what it means, that the eggs have the same break resistance. Well, we want to identify that lowest floor, the floor number 7, for example, or it could be 15, 21, or there may be no floor, the throw from which the eggs will not survive. In other words, if eggs are thrown from the 100-story, from the very top floor, they will survive the fall. So all these possibilities are on the table, and we want in this challenge the minimal number and the corresponding testing scheme or the testing algorithm for the egg drops that will determine with absolute certainty, there is no probability, non-trivial probability involved in this case that will detect with absolute certainty the lowest floor, the fall from which either of these eggs will not survive. Again, this problem can be solved in a number of different ways, but because right now we're studying the mechanics of the reverse order problem solving approach, we suggest that you try to solve this problem using the reverse order problem solving approach. And again, on this channel, as a reminder, precisely because we want to nurture, showcase, and develop the ability to think out of the box in mathematics, theoretical physics, and computer science, we're not interested as much in the answer. Of course, the answer is important and interesting, but most of all, we're interested in the story behind, the story of how and why the answer of this or that problem comes to be. And this is the first class citizen on this channel. So we suggest that you try to develop the solution and develop at the minimum the proof that the number that you come up with is indeed the minimal number of egg drops that will detect the lowest floor in this building, the throw from which the eggs will not survive. This is it for this episode. Thank you very much for your time. Thank you for watching, and I'll see you in the next episode, Season 2, Episode 7, in which I will discuss the solution and the corresponding proof of our first computer science problem, C2S1.